Okay, so this is the last set of this resonance structure problem. We are talking about PCl4. So once again, this is a PCl4 with a positive 1 charges. So you have to account for essentially the overall positive charges this one is having it to consider the formal charges on each atoms and so on. So let's look at trying to identify where's the phosphorus atoms are located. This one right here. So therefore, this is on the 5th column. And what about the chlorine? Chlorine is right here, which is a 7th column. Okay, so I think that we are on top of things. So therefore, number of electrons, valence electrons. So phosphorus is 5, and the chlorine, there are 4 of them, and each of them has 7 valence shell electrons. And then you have one last thing to consider, which is a positive charge. So you need one less electron for this molecular species. So that will make it 32 electrons. So you have 32 electrons, and then now you're looking at the symmetries. Looks like the P should be in the middle, and then you have a chlorine. There are 4 chlorine, so I can just put the chlorine like that. And please note that overall molecule has a positive 1 charges. So that's my starting point for this. And then just like usual, what I do is let's make a bond. So 1, 2, 3, 4. That makes it 8 electron that I consume, and then I ended up having 24 electrons left. And then what I do is let's use a blue dot this time. So each outside in, so outside 1, 2, 3, 4, 5, 6, 7, 8, including the bond. So chlorine, which is a halogen, they just make up they need 3 pairs of lone pairs to satisfy the octet rule. Same here. So it's pretty much the same. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So with 3, 5, 6, so they make it up to satisfy the octet rule by 6 lone pairs and the one in the red bond, which is 2 electrons. So that's 8 electrons. So by doing so, by using all the blue dots, which is 4 times 6. So 4 times 6 is, you have 24 electrons, right? So this is essentially 4 times chlorine with those dots, right? So those are the lone pair electrons, okay? So you make it up, and nothing left. So there's nothing left here. And if you're looking at the formal charges, it's actually quite useful to know when your halogen in the 7th column form the single bond with this 3 lone pairs, their formal charge is 0. But I want to show you why it has to be 0. So formal charges, chlorine means 7 minus, once more, this is a number of lone pair electrons, right? Plus half of number of bonding electrons, right? So 7 is a number of valence shell electrons as a neutral atom for the chlorine. And then how many lone pair electron? I see 6. How many bond electron? The one in the red, I see 2. So 7 minus 7 is 0. So no formal charges for this one. So like this one has no formal charges. And then as I like to do it before, this overall, this has a molecule has a plus 1 charges, and the summation of formal charges on this molecule, on this atom, on this molecule, has to be 0. So, this one must be the one in the middle, which is the only one whose formal charge is unassigned, must have a +1, right? So then therefore the summation of formal charges on atoms has to be the same as the formal charges of the molecule. So that can be the one. But to make sure that we are on the same page, I can use the same thing, the formal charges equation, phosphorus. Phosphorus, once again, you are on here, which is a fifth column, so that's 4. 5 is a neutral, 5 electrons, so that's a number of valence electron for phosphorus. And then minus, and how many lone pair electron do you see? None. And half of bond electron, you see 4 bonds, so that's an 8 electrons. So 5 minus 4, that's a +1. So that's the way to find out, and then this is to confirm my Lewis structures. And this one is true. This one is probably the most the stable resonance structures, because some of you might think about, and this is the answer. Some of you might curious, saying, "What about?" I think that in the previous lectures, I have seen you kind of push the lone pair electrons around, right? So here's an example. Then you are perfectly fine to consider that as a possibility, right? I encourage you to actually consider the possibility. So my possibility is, well, okay, why don't I have these two form the double bond? And then let's see what happens, right? So then what happened is this P lost the formal charges, and then the chlorine now develop plus formal charges. And the rest of them, I will just keep it the same. So this is a chlorine, chlorine, chlorine. So now I have to consider this one is now no formal charges. So which one do you prefer? Do you have no formal charges on the chlorine and the one in the phosphorus in the middle, or the one here? So this one is actually chlorine, known to be as a electronegative atom. So they like electrons, but you are making this one electron deficient. So this one is very, very unstable. They are not happy. Okay, they are very mad. Like I need more electrons, and you take the electron away from me. So this is not a good scenario. On top of that, this is a although it's you can have more than 8 electrons, still 8 electron is a good one. You are enforcing them to have 10 electrons, right? You have a 5 bonds, so 10 electrons. So it's a extended octet rule. Can it have? Yes, it can have, because of the this is only this one must satisfy the octet rule, because 2s and 2p is the only thing they can have, not 2d. This is not possible. So 8 electron is the maximum they can have, but this one is, for example, 3s, 3p, and 3d. So still prefer the octet rule, but they can have a room having more than 8 electrons if they need to. That's an extended octet rule or expanded octet rule. So yeah, this is still feasible, but it's not. So for that reason, this one is not really favored, right? So that's not really favored, and this is truly the good form of the resonance structure. So that's the answer for this resonance problem, for this resonance question. Thank you for your attention.